Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we are going to design a 4-into-1 T4 collector flange. So a little while back, we did a video on using 3D sketching to help plan out building an exhaust manifold. Now, I did have a couple comments about the collector I used in that. It was never really meant to be a true part of the series, or of the video, I should say. But there were some comments about it not being a realistic part to manufacture. And while you can manufacture this part, it certainly isn't feasible or realistic. So I figured we'd just circle back and we would make one that is realistic, that is feasible, to show you how to design it and also how much it costs. And also, we're going to talk about designing a 3D printed template that will let you sort of mark and determine where each of these pipes is cut. So I have this flange in my hand. I have the 3D printed sort of guides. I've got the pipes. I haven't cut them yet. So I've got everything on hand, and we're going to walk through how this process works. I'll talk a little bit about price and give you some more information about, the own process of doing this yourself. So first, I do want to mention that this video is sponsored by PCBWay. We've done a video in the past with them on a printed circuit board for a previous project, and they wanted to do another sort of sponsored video. So this one is sponsored by them, specifically their CNC machining side. I will talk a bit more about PCBWay later in this video, but just keep that in mind that they did sponsor this video, and we are going to be talking about them a bit more. Before you ever get started designing your parts, I think it's important that you take a look to see what's currently available. While this part costs under $80 plus shipping to get CNC'd at PCBWay, there are companies that make these parts. So if you can find what you're looking for without having to design, have it machined, and you've got a reputable company that you can work with, I think that that's a great option. So this company, Maven, is just one I came across. I'm not affiliated with them. I haven't reached out to them or anything like that. But they do make several different types of collectors that look like they're really well built. Everything from singles to dual open and divided T4 flanges. But again, you have to look at, one, the cost, which I think $210 is a good deal for this part, and whether or not it's the thing that you need. All right, so in my case, I really wanted a 4-into-1 T4 flange, and the only ones that I could find available were pre-welded, and the pipes were sort of cut and welded together. And I didn't love the transition, and I didn't really like the way that they were constructed. So I thought it was a good opportunity for us to walk through how to design that ourselves. But I think it's important that you do take a look at what's available, see if there's something that you can just buy that's already pre-made and can help you along your way. There are plenty of companies that have these different sort of build your own manifold kits, and there are plenty of parts out there that are available. Now, the actual bends that I got are 304 stainless. They came from this company, Ace Race Parts. Again, not a company that I've contacted or worked with. I paid for these myself, and the quality is really great. Each of these pieces came wrapped in plastic with end caps to protect them. And I had all the information I needed here about the bend and the wall thickness for me to design the part in 3D. Now, they were $8.50 a piece. So again, doing this in stainless does add up. It's not cheap, but most of the parts that I found are 304 stainless, which is not probably the ideal stainless for high temperature applications. 316, 321, those sort of more exotic stainless steel materials tend to be used on things like brake rotors and other applications. But 304 seems to be pretty common in the exhaust manifold market for these parts. So the flange that I had machined is 304, and these bends are 304 as well. So I'll leave a link to Ace Race Parts, this specific bend, and I'll also leave a link to Maven. Again, not affiliated with them at all. I just happened to come across them. So now let's talk a little bit about the process of designing this. So this is going to be a multi-axis part. And what I mean by that is we're transitioning from 4 round sections and we're going into a squared section. So the way that I have this designed is so that there's a small lip at the top and there's a recess for where the pipes are going to fit in. And the main reason for doing something like this on an exhaust collector or any type of flange that you're going to make that needs to be welded is the fact that the heat that's going to get soaked into the base flange is going to make it very difficult to weld to thin-walled parts. So if you are using a TIG welder, you may need to preheat the flange, but having this thinner section up top gives us a better chance of getting a good penetration weld on both sides without burning through the stainless steel tubing. So that's something to keep in mind. And if you look at other companies that make these types of flanges, there are ones that are just flat flanges, which of course would be a lot easier to machine. And there are ones like Maven Performance that have this raised lip. And I would assume it's for the same reason, to keep the welding process a bit easier. So I have a 3mm, I think, wall here. That's going to be plenty enough room to leave a substantial bead of weld on there. And I used 45-degree bends because I thought it would be easier to be able to weld in between. If I was just to use straight pipes, which is of course an available option, it would be a bit harder to get in here and weld. And I wanted to be able to weld everything from the outside. So you can see the way that these things are arranged at 45 degrees. It allows us to get a full penetration weld with a standard TIG torch. You may need to use a larger cup to extend the tungsten out a bit farther to get down in here. You could also weld from the inside if needed before you attach it to the flange. That is a possibility, but again, these are all considerations and things that we need to think about when we're designing. So with all that out of the way, let's go ahead and start designing the part ourselves. I'm going to be using the metric system just simply because a lot of the reference dimensions that you get for these flanges are going to be metric online. So a lot of times it's easier to do that. You can use the imperial system if you want, but we're going to get started by first doing our base flange. And I'm going to do the flange in its entirety, even though we're going to end up doing a sort of a lofted transition from the 4 pipes down to the rectangular opening. I want to start with it as is. So we're going to get started with the rectangle. I'm going to use a center point rectangle, and we're going to give it a dimension. So the overall dimension of this is going to be 115. I'm going to hit tab and 95. So that's the full rectangle. From here, I'm going to do a fillet inside of the sketch, which I don't typically do, but in this case, I'm going to do everything in the sketch. I'm going to select these corners. You will get some warnings because it's not happy about the constraints that you're sort of killing in this case, but right-click and OK, and don't worry about the warning. So Fusion has kept the dimensions on our reference lines, and there is automatically some constraints that will keep these in line with that corner. So I'm not too worried about that. I can't grab this and pull it around. Everything is still fully constrained, so we're good there. The sketch itself has the pencil icon, which tells me that it's under constrained, but I haven't found anything in the sketch that I can grab and drag. So I think it's just mad that it broke some of those original constraints, but everything is still fully constrained here. The next thing that we need to do is another rectangle. You can use shortcut keys. For the purposes of these videos, I'm going to try to avoid shortcut keys just to slow it down a little bit. And the inside is going to be 75.2 millimeters. And we're going to hit tab to get to the next one. And it's by 49.2 millimeters and hit enter. So this is going to be the sort of internal section here. And again, this is going to have fillets on it. I'm going to use that same 10mm fillet. There isn't actually, I haven't found a reference drawing that lists a radius value for these corners, so I'm just assuming 10mm. It's better for us to make it, in this case, 10mm, and then if we have to manually grind it and sort of port it back to better fit the hot side of the turbo, then we can do that. If you make it too small and you can't really add more material unless you're welding and then grinding it back down. So I find it's a bit better to kind of exaggerate this right now with a 10mm radius. And then again, I can always grind it back later as if I'm trying to port match it. So now that we've got the inside and the outside, I'm going to toss the holes in here as well. Now, generally these holes, because they are going to be tapped, they would be added later with the hole tool, but we're going to use the thread tool to adjust them. So what I'm going to do is dimension this, and this is going to be 10mm diameter. It's going to be an M10 thread. So in this case, just doing a 10mm circle right now will be fine. When we use the thread tool later and we define a thread, it'll actually reduce the hole size for us to the appropriate drill size. Now we need to determine where that's going to be. The way that this typically works is with a rectangle. So I'm going to go ahead and add this rectangle. The bolt spacing is 82.5 wide by 70 millimeters tall. I'm going to double click on this and make it construction. And then I'm going to just simply drag this to that corner point. It can be tricky because there are a lot of lines happening in this area. So make sure that you zoom in if you need to. And then what I'm going to do is I'm going to just create 4 more or 3 more circles. I'm going to set all of them equal to this original. And you'll notice I go back to the original each time. You could sort of work your way through or select all of them and make them equal. But one thing I find is setting these constraints back to the original is important, because if I ever happen to delete one of them, that could break the constraints to the rest of them. So that's why I tend to go back to the original when I'm doing things like an equal constraint. And then I'm just going to drag them to the corners where they need to go. You could, of course, draw them in the corners and then apply the equal constraint. I find that when sketches get like this, they get to be a little bit busy with all the dimensions and the construction lines. So I tend to do things a little different in some cases. So in this case, drawing the circles on the side and dragging them where they need to be. So that's everything we need for the flange. Now we can extrude it. And I'm going to extrude it up 12 millimeters. You have to think about stock size when you're doing something like this. And if you were just going to have this, say, laser cut or water jet and then tap the holes, if you do, I would suggest water jet, not laser, because the laser will change the sort of the tempering of the stainless. But if you were going to do that, you'd want to keep it flat and sort of a nominal stock size that makes sense. If you're going to be CNCing a part like this it's going to have a raised lip on it, this 12 millimeters isn't super critical. You just want to make it thick enough that it can soak the heat without deforming. So 12 millimeters is going to work for us in this case. The next thing that I'm going to do is sketch on the top face here. We're going to right click and create a sketch. And I'm going to design the 45-degree mandrel bent tube, but I'm going to do it from the origin. So I'm going to do a circle at the origin and a second one here, and then we're going to zoom in a bit. I'm going to hit escape, hit D on the keyboard, and we're going to dimension the outside. Remember, this is 1.625. So if you want to, you can always type in 1.625 inches, and it'll automatically convert it to millimeters for you. I'm going to have to hit escape here because this is going to be the ID. You want to pay close attention to whether or not you're dimensioning the inside diameter or outside diameter whenever you're working with tubing, whether it's something like a Schedule 40 tube or if it's a DOM tube or something like this. You want to make sure that you are confident in that diameter size being either the inside or the outside. So for us, now we're going to have a wall thickness. And again, if you go back to, in this case, Ace Race Parts, this will tell us here exactly what, I'm going to go ahead and click on this. It'll tell us here that we're using 1.625 size. So the outer diameter is 1.625. The wall thickness is 0.65. And it gives us a centerline radius of 1.875. So 0.065 is going to be the thickness here. So 0.065 inches. So you have to make sure you put IN after it because we are dealing with the metric unit system. And again, it's going to convert that for us. If you double click on it, it'll show you the inch value, but display the metric value for us. So I'm going to double click the mouse so that I'm going back to a sort of a fit to screen view. The second thing that I want to do here, which isn't strictly required, is I want to draw another circle. And I'm just going to place it over here, hit escape. This one is going to be equal to this one. So select it, hit escape. It's also going to be construction. You can use X on the keyboard. The reason that I want this here is because this is going to allow me to kind of roughly position this. The reason that this is important is because we're going to have to design this 45-degree bend and then move it into the correct position and pattern it. So the reason that I want to do this is I want to get a rough idea where this is going to be located. And this will also give me an idea of this overlap. Now, it's not going to be a perfect location, but this will help us to sort of better identify where this is. And if you want to fully dimension this, you can, because you can always come back and edit that later. So for example, if I knew that I needed this height to be something like 5.625 millimeters, I'm just making up numbers here, then we could play around with that. I'm going to hit escape and then drag this over. And what I'm looking to see here is how this interacts with that rectangle. So I'm going to leave that underdefined. It's just kind of a concept I wanted to make sure that we understood, because having a reference for where this is going to get moved to can be extremely important, because the move tool, the align tool, you can do things like to, from, select points. The second thing that we need to do is develop the centerline radius. So we're going to start a new sketch. This time we're going to be on the front plane. I'm going to rotate this around just a little bit, and I'm going to go to project include and project this point. Now, if you're working about the origin, if we had extruded this flange 12 millimeters in the negative Z direction, then we would be working directly at the origin and it would be totally fine. In this case, I just want to make sure that I've got the reference for the center of that. So I'm going to create an arc. So we'll go to create arc, 3-point arc. We're going to start here, come up and to the left, and then just create this. We're going to add a dimension. So this is 1.875 inch radius. And now we need to define this in some way. Currently, we don't know that it's going straight up. We don't really know if it's 45 degrees. So we have to figure out a way to fully constrain this. The way that I do this is by using the line tool. I'm going to bring a line that's tangent here, and then a line that's tangent here. So we need to find our tangent constraint, make sure this is tangent with that. I'm going to make sure that this is vertical, and then I'm also going to make sure that these two are equal. I'm going to hit escape, then I'm going to make this line construction, I'm going to make this line construction. Now, we're not fully defined yet because this angle can change, so we need to use our dimension tool to dimension between here. It's telling us right now that this would over-constrain the sketch, but that's not strictly true. The reason that it's saying this is because we have applied some constraints that are limiting what we're doing here. So temporarily, I'm going to delete the equal constraint here. This will allow me to dimension this angle, and this should be 135 degrees. The reason it's 135 is because we did 45 degrees basically from vertical. So what we're actually dimensioning is the angle from this line to this line. So we have to basically go from 180 minus the 45, and then we get 135 on this side. So now that we've got this, you can see it's fully defined. We didn't need to use that equal constraint between these two, and that caused it to be over-defined. So when you run into issues like that, just take a step back, delete a constraint or two, apply the dimensions that you know you need, and then see if your sketch is fully defined. We're going to finish the sketch, and now we can sweep. So we're going to select the sweep tool. This will be our profile, and this will be our path. It's going to be a new body. It's not touching anything, so it's not going to automatically try to join it, but make sure that it is a new body. So there is one of the four that we need. The next thing that I need to do while it's still centered is I want to rotate it. Now, in my example, I've got the four bends rotated away from each other at 45 degrees. The reason for this is because this 45-degree bend is not very much. It's still plenty for us to get pipes to interact with this thing. But this is actually very important if you are working with, let's say, a front mount and your turbo is shifted more towards cylinder 1 or cylinder 4. It's not centered, or if you're working with some sort of interesting turbo orientation, you need to actually think long and hard about the angle that these are going to come into the collector, because that's going to impact what you do downstream. Now, each of these little bends, again, they were about $8.50, $9. So cutting a bunch of these is not an option. It's not a trial and error thing. You want to get it right here. So what I'm going to do is I'm going to take this and I am going to rotate it 45, but I don't want to rotate it from this point. I want to make sure that I set my pivot at the origin. So you're not going to be able to select this. You're going to have to rotate this thing around and just find a center point that works. If you can't, you can always turn on the actual origin and we can set it here. So what we're going to do is we're just going to put it right at the actual origin. And this gives me a good reference. So back to a top view, I can now rotate this 45 degrees. And then we'll say OK. I'm going to hide the origin. I'm going to go back to my sketch. This is going to be sketch 2. This is the location I want this to be in. So when I'm trying to move this part, there are a couple things that I think that we should mention because Fusion doesn't do this great. And what I mean by this is when we select move copy, and actually we can go back and we can take a look at the one here. It doesn't record the fact that we moved the pivot point or that we rotated 45 degrees. For whatever reason, it doesn't capture and present that data when you use the move command. So moving something to a random position, you can delete the move feature and you can go back to that original position, but you won't be able to edit and know, okay, I moved this 5 millimeters. I really needed to move it 6. You just won't have that data. You can always go back to the original sketch and try to measure the distance from where it started and where it went to, which is kind of a benefit of starting at the origin. But just keep that in mind. The move tool doesn't actually record that for you. So what we're going to do is we're going to move this body and we're going to go from point to point. So I'm going to select this as my starting point and this is my ending point. So this will preserve that 45-degree rotation, and it will allow us to move from our selected point at the origin to that reference point we created in the same sketch. So again, that's the reason why we use that. Is it needed? Could you just manually move this thing around? Sure, you don't need to have that as a reference, but this is a good way for us to at least build it out. Now, I'm not saying that this is actually going to be exactly where this needs to be. It's possible that we need to make some changes, but it's a good starting point. Now I'm going to take this and I'm going to mirror it. And we want to mirror this about the right plane, and then we also want to mirror it about the top plane. So right click and repeat. We're going to mirror both of these bodies, and this time we'll go this direction. And it's saying join. I'm going to do new body for now. But the reason I want to do this is because there's a big gap in the middle. We can't have that gap, and there's too much overlap between these. We can see that we need to preserve the outside diameter of both of them. So what this means is I need to go back before the mirror, and I need to manually move this body to a different location. So we're going to go to free move, and I'm just going to move it to the right and down. And what I'm looking for here is I want to make sure that I'm still kind of trying to stay within the confines of that rectangle. And I'm going to say OK, and then go back in front of the mirror operations. There's a little bit of a gap here, so I still need to move it to the right more. And we've got our overlap here. We can see that. And so we just need to move it a little bit more. So I'm going to edit this feature and manually move it to the right and down and say OK. And we're getting close. We got a little bit of an opening here, which is fine because we're going to do a 3D blend. And this is fine here. But the middle, I really want to make sure that they're overlapping. So I'm going to double click and edit this feature and move it to the right just a little bit more and say OK. All right, so now we're looking pretty good. We've got 4 into 1. We're pretty close to the corner here in the rectangle. And I'm happy overall with their locations. Now that we've got them in the right spot, we want to go to boundary fill. So we're going to select all 4 of these bodies. And then we want to select the cells. These are going to be the cells to keep. So basically what we want is we want to keep the majority of it. So I'm going to select the centers here. And what we want to remove are basically going to be these 3 sections down here. This is probably going to take a little bit of time to play with, but because the pipes overlap in the middle, we have to be real careful with what we keep. I'm going to try to keep the upper sections in the middle here, and I'll try to keep these upper sections here as well. And then I'm going to say OK and just see what the result looks like. So we're going to get rid of body 2, 3, 4, and 5. And actually, let's hide the flange as well. And let's just see. So that looks pretty good. There's some kind of weird stuff going on in the center. That's okay because that's probably an area we would want to grind away. So what we can do is we can select these inside faces, just go through and select all the ones that you can see, rotate this around. And once I have all of them, I'm going to hit delete on the keyboard, allow it to patch that. And then I'm going to use push or press pull, see if I can just bring that back. All right, so that'll give me, basically that'll let me cut or manually grind where that needs to be. But everything else looks pretty good. The smooth transitions, this is all one body, kind of rotated around. And it looks pretty good. I think this area, we can see there's a problem in the bottom center. Let's rotate this around. There's a small hole here. So I'm going to undo this, maybe pull it back down a bit. And what that tells me is that I might want to consider moving these to the right a little bit more. And that way we would have basically it wouldn't be so deep right there in the center. For the purposes of what we're doing, I think it's fine. But again, this is an area where you should spend a little bit of your time making sure that you are very clear on the orientation of each of these. They don't have to be 45 degrees away. These two on this side could be facing 90 degrees. They could be pointing straight down. These could be pointing straight up. These two could be pointing roughly the same direction, but you got to just make sure that you have the complete outside diameter. So that way, after you lay a weld bead, you still have the correct thing to weld to. I'm going to select the 4 original bodies, right click and remove them. So that's going to put remove feature in the timeline for us. Another thing we should consider doing, which we haven't done yet, is save. So I'm going to go ahead and save this. And this is going to be turbo collector T4. All right. So now we're getting pretty far on. We really need to think about where these pipes are going to sit in 3D space. And then we need to think about the transition. So what I want to do is I'm going to rotate this to the side. And I need to move them up. So again, we're going to use move copy. I'm going to click this vertical direction, which will bring up my dialog, and I'm just going to put 5 millimeters in there. So 5 millimeters is going to be basically how high that lip is going to come up, and then it's going to actually come up a bit higher, but that's how high this is going to be above the main portion of the flange. And again, the main reason for this is, well, 2 reasons actually. One reason is to give us more distance for the transition between these 4 pipes to the rectangle. The second is to ensure that we've got a thinner section when we're welding to it. We don't want to weld directly to this because it's just going to be too much heat and it's going to end up causing more problems popping through the thin wall tubing. So unless you preheat everything, it's going to just be harder to weld. The next part is arguably the fun part. We're going to make the transition shape from this down to this. Now, there are a couple of things to consider. One is, do we want to actually have a fillet or blend on the pipes, even though we know that that's not going to be how they actually get manufactured? They'll have welds. I would say no. I'm going to leave this a sharp corner, but I could see the argument for blending these together, however big the weld bead will be, and then that is going to be that rounded profile that we use. For our purposes, I'm going to leave them sharp, and I want to start a new sketch by right-clicking and selecting that. We're going to hide the flange for now. And basically what we want is this outside profile. Now we already get this outside profile when we create a sketch on this face, but I generally like to go and do project for those edges. And the main reason for that is because the profile you get from creating a sketch, while it is useful, it will not give you a sort of a good visual reference. So we do have this edge here. If we double click it, we can convert it to construction, for example. That is true about that outside profile as well. But again, projecting it just makes it a little bit easier to see. So now that we've got that sketch, what we're going to do is sketch on the bottom of the flange. And once again, we've got this section here. I'm going to project it. So you can use P on the keyboard, or you can come up here and select project, double click this edge. Or in some cases, you may need to work your way around and manually select it. I'm not sure why that is, honestly. You would think that it would be a bit better. Let's hide this other sketch. It's getting a little crazy. So I'll just grab these edges, work my way around. I really wish that the tangent selection was a little bit better in Fusion. If you're in a manufacturer workspace and you're doing toolpaths, you can hold down Alt and disable the tangent chain selection. In sketching, it's kind of hit or miss, honestly. So I'm not really sure why that is. So now let's hide the bodies and let's go ahead and bring both of these back. And we're going to create a loft from this one to this one. So solid loft is a new body, and we'll say okay. So basically what we're going to end up doing is we're building the section that we're going to cut away from the base of the flange. Now, I know right now the base of the flange has this opening, but we're going to select everything on the inside, holding down Shift, and then make sure that we are in the solid tool set, and then we're going to hit the delete key. So what that allows us to do is it allows us to have this core that we're going to use to cut away from the rest of it. Now, before we do that, let's remind ourselves that this is perfectly matching the outside shape of the pipe. So what we're going to do is we're going to create a thin wall version of this using shell. So I'm going to select the top and the bottom. It's going to be 0.065 inches and hit enter. So now the pipes in this should exactly match. And the main reason that we're doing this is because all we're concerned with at this point really is this inside. So we want the inside transition to be perfect between these tubes and with the base flange. So now what we're going to do is use boundary fill again. We're going to select both of these solid bodies, and then the cells that we want to keep, notice that there are these two cells. This is tricky because there's actually three here. So if we select one of these and we hold down the left mouse button, it brings up this list. Now this cell list here is empty for whatever reason with boundary fill. I wish they would fix this. I'm not sure why it's like this, but basically what we have is we've got the three check boxes. What will happen is we'll need to play around with this a little bit to make sure that we have the right selection. You can see that it was not correct, so I need to go back. And then I'm going to left click here, hold down the left mouse button, and try this bottom one. And you can see now it gave us this sort of transition shape. Let's hide the original. And you can see it's still missing that last piece. So we're going to edit this and hold down the left mouse button. And let's select this middle cell and hit OK. And what do we have here? All right, so now it looks like we got everything we need. So I think boundary fill is an extremely powerful tool. I really wish that dialog box was a little bit better because it does make it difficult for us to do things like that. Let's do a quick save, make sure we don't lose anything. We're going to take care of blending and filleting this stuff a little bit later, but right now we have to realize that we've got these tubes here, and machining this is not going to be ideal or possible or feasible because this is sort of rolling underneath and we've got a square corner down here. It just wouldn't work. Now we could put a large fillet on there or do something like that, but really what we need to do is build this flange out and down, and we can do it a couple different ways. So I'm going to do a sketch on top, and basically what we want to do is use offset and offset this outward. Remember I said that I had about a 3mm wall on the part. That's going to give us enough material that we can build this 3mm section all the way down to the base, and we can also build it up. When we think about building this out with the extrude tool, it becomes actually pretty difficult. So for example, if we say extrude and we extrude this down, what ends up happening is there's going to be a gap between some of these walls because the inside shape is tapering inward, and what we're trying to do is extrude this down. You could taper this outward. You could say make it 10 degrees or something, and that would allow you to taper into the original section and outward. But then when you're machining this, now you're going to have to machine this tapered section, and there may be areas like this that you miss or that you end up cutting into the inside. So instead of trying to do this with an extrude, which again, it's possible, you can try to do like extrude to next, but really what I'm going to do is start to use some surfacing tools. The reason for this is because I think it's important whenever we're working with complex shapes to have a good understanding of surfacing tools, how they can benefit us and how they can help. So I'm going to take this and I'm going to extrude it down. We can go exactly 5mm. We could go a little bit more if we wanted to, but we need to go at least down to the surface because it's going to be a trim tool. What I'm going to do is I'm going to actually make this two sides because the other direction, I want to go up 1mm. So remember in the original one I showed you, we had a 1mm raised lip. Now that raised lip is there to help locate where the actual pipes are going to be. So we're going to say, okay, and now we've built this wall that goes straight down and also 1mm up. Now that we're on the surface tools, we can select these faces holding down shift. Let's rotate this around. and hit delete. So what happens that's different when you're in the surfacing tool sets versus in the solid tool sets is when you select and delete a face, you're actually removing it and converting this to a surface body. If you were to do that in the solid tool space, what would end up happening is it would actually try to remove the face and patch the geometry to keep it a solid. There are some arguments for tools like replace face that could potentially work, but it's complicated because we've got multiple non-tangent faces that we're dealing with. So again, I think surfaces is just the right call. So what we're going to do is go to create, ruled. I'm going to select this edge. We're going to go normal, and we're going to go 1 millimeter. So once again, we're building out that 1 millimeter lip, and we can patch this top section, but we need to trim or get rid of some of this bottom section. So using our trim tool, we're going to select this extruded surface and then select the inside face to remove it. It should show up as red. And now you can see that we've got that. And then next we're going to use the patch tool. Now the patch tool doesn't allow us to really select these two regions. It does work if it's a sketch. So if we created a sketch at this height with the inside and outside profile, we would be able to patch it properly. But what we need to do instead is use our trim tool using this 1 millimeter ruled surface and just get rid of the inside. So now that we've got everything, we're going to stitch it together, select the main body, this extruded section, the patch on the top, and this ruled surface here. And as soon as we do that, it should turn it back into a solid body for us. So now we've got a solid body and we're almost done. There are just a few last details that we need to take care of. But let's go ahead and save this. And now what we need to do is we need to take care of rounding off some of these corners on the outside, on the inside. We need to figure out what kind of a radius value we want here and what kind of a radius value we want here. These are external corners, so they're not going to be subject to the diameter of the tool. This is going to be, again, a multi-axis tool path, so that's going to have to get blended with a ball end mill or a lollipop style mill or something. This one here, because this is flat, will likely be done in a more traditional 2.5 axis tool path. So we can just make it a radius value that makes sense for us. I would say that we want to keep it relatively small. Otherwise, we're going to have a large gap that we need to fill with weld. So let's go ahead and use the fillet tool. And let's fillet these outside vertical edges. You can select through as long as you still have the default sort of selection manager tools on. So by default, the selection filters will allow you to select through, and we can just add a fillet that makes sense here. 5 millimeters looks okay. I also want to add a large fillet here, maybe 5 millimeters. Keep in mind that you can use plus and you can add multiple fillets at the same time. So for example, if we come in here on all these corners, we could also leave these sharp. I think it's a good idea to just put at least a small, let's say 2 millimeter fillet there, hit plus, and then we can add a fillet to these edges here. I'll rotate around. And there. And let's try 2 millimeters, see what that looks like. That looks pretty good. 5 might be too big on the outside. That's okay. We're going to just leave it for now. And a couple more things that we need to take care of. These holes need to be tapped. So we're going to go to create, thread. We're going to select the holes, hold down control. And notice that it's automatically using an M10 because it knows that it's a 10 millimeter hole. So M10 by 1.5, it's going to be a fairly common thread size for this. We're going to say okay. And again, it reduced that hole size. So if we inspect this and we measure the hole, instead of being 10 millimeter, it's 8.5 or 8.526. So that's going to be the appropriate drill size when this goes to get machined. They'll be able to drill the correct size and then run a tap through it. Another thing to consider with this is that we probably want to break these edges. Now, generally a part like this, you could say, break edges or tumble finish. But if you want it to be something more substantial, like a 1 millimeter chamfer, then you will need to manually add it. Keep in mind that things like this tend to increase the cost of machining. So if you are working with a local machine shop instead of PCBWay, then make sure that you do factor these kinds of things in. Basically everything that we do here can have an impact on the cost. For this, I'm going to say okay. And I think everything looks pretty good. I think the transitions look good. Again, this is a multi-axis part on the inside. Everything on the outside can be done with a traditional 3-axis machine. The inside could potentially be done with a 3-axis machine from 2 different orientations. So if you were trying to machine this yourself, you could get to some of these areas. So for instance, these faces here, and then when you flip it over, you can get to the rest of the areas from the bottom, but that would be pretty tricky. A tool like a lollipop mill where it tapers in and then goes back out may allow you to get this from one direction, but it would be pretty tricky. So now that we've got this, I'm going to bring back, actually we don't need this anymore. We'll right click and remove it. I'm going to bring back the pipes. I'm going to rename them as well. Pipes, flange, and this other one here, this is the original flange. We don't need that anymore, so I'm going to right click and remove it as well. So now that we've got the pipes and the flange, we need to think about a template that we can use to figure out where we need to cut these pipes. So that's actually a pretty easy part. I'm going to go to Surface, Create, and Offset. I'm going to select just one of these, and then I'm going to offset it. I'm going to do this 0.5 millimeter. And the reason for that is because this surface is going to have to slip over this pipe. So I don't want it to be exact. I want it to be have a little bit of a gap. And then we can use Create and Thicken. And then you need to think about what you can actually print. So 2 millimeters is going to be fairly easy to print. I'm going to say okay. And then I'm going to hide the pipes. So basically, when you go to 3D print this, and I've already printed a few of these, this face here will be on the build platform, and then everything here will build up without supports. It actually works pretty well. And then you just need to repeat this for the other side. So this is going to be, this one can be used in 2 positions. So it'll be the same, basically 2 pipes can be cut with that. And then we'll need one over here because that's kind of the mirror of it. So do the same thing. We'll do an offset, 0.5 millimeters, and then this surface will thicken 2 millimeters. It's going to remember our settings from last time. All right, so now this is side 1 and this is side 2. So now that we have everything designed, I think it's important that we next talk about PCBWay, the sponsor of this video. So as I mentioned, PCBWay is a company that does PCBs, obviously. We've done a video for them on that. They do CNC machining, they do injection molding, they do 3D printing. So they have a lot of different services that they can offer. Now, I've worked with PCBWay a couple times, and I'm in constant communication with them during these projects, and I've had a really good relationship with them. And I think that it's important that we think about these things when we're looking for a supplier or a vendor for our projects. One other thing that PCBWay does that's pretty nice is they have a share and sell option. So if you are designing products for, say, 3D printing, or in this case, CNC machining, or even electronics, you can add those to their share and sell sort of portal. And that will allow you to get a commission when those things are sold. That keeps you from having to machine things yourself or 3D print them yourself. You are able to just upload the digital design with information about it, how it works, a video if you need, and then you basically just have a way to collect some commission on those designs. Now, obviously, that's different is if you were to machine and sell parts on your own versus using their service, but it is a nice option for those of us that maybe don't have direct access to a machine or that functionality on our own. Now, as I mentioned earlier on in the video, we have to consider cost, and having this part machined, which again is, I firmly believe, is a multi-axis part without doing a lot of work to try to get it to work on a 3-axis machine, was $78 plus shipping. So all said and done, under $100 to get a custom CNC'd 304 stainless flange that can be used for the exhaust collector. Now, I have talked with other rapid CNC companies in the past that have wanted me to do sponsored videos. I've basically have turned most of them down, and simply due to the cost aspect of it. I cannot in good conscience tell somebody to get this part machined for $1,200 when you could get it machined for under 100. So I think it's important that we consider this. PCBWay is a Chinese company, and I do support U.S. manufacturing, of course, but it's just a factor of cost for building a one-off part like this. And as I mentioned earlier in the video, I've programmed and run CNC machines. I've worked with local machine shops on projects, and I cannot think of a situation or a scenario where a shop would take on this job for less than several $100s. So you may have the option to use something like an H-Tech school or community college that has a machining program and allow them to machine these parts as part of their curriculum. But other than that, you're really stuck either having access on your own or using a rapid service like PCBWay. Now, I've had really good experiences working with PCBWay, and I do, strongly suggest that you at least quote and check them out for your projects, and then make the decision for yourself what's right for you and for your own projects. But for us, now that this part is done and uploaded, let's make sure that we save it. It took about 8 days to get machined and sent to me. It was actually machined relatively quick. The quality control phase was probably the longest part of it, and then shipping to get it here. So a couple of other things that I do want to note, because this part has tapped holes, if you are uploading a part to PCBWay that has tapped holes or any additional requirements, they will ask you to do a detailed drawing. It can be fairly simple, really just needs to call out where the holes are, and it needs to call out the thread type. Other than that, it's pretty straightforward. If you aren't going to be doing any tapped holes, if these were through holes, then you wouldn't need to provide a detailed drawing. Now, some other things that we should consider as well, when you're uploading a file to PCBWay, there's all sorts of options for material, finishing requirements, things like anodized or powder coated, whether or not you just want it as machined or if you want additional finishing. You can determine and dictate all of that at the time that you're getting your quote. I just did this as the lowest possible option, as machined, no additional requirements within their default tolerances, and everything's great. I can notice some tool marks where I believe they removed the fixture that they were using to hold it for multi-axis machining. But again, I did not specify any surface finish requirements or any additional finishing, so I ordered it as machined, and that's what I got. So with all that said, let's go ahead and take a look at cutting the pipes and getting everything fit together. Now, the process of cutting the pipes is fairly straightforward. Using the 3D printed jigs, we're able to use just a Sharpie marker and mark and make our cuts. Now, I do suggest that when you're doing this, you are careful because these are relatively small, so it is going to be tricky. Whether you're using a bandsaw, if you're using a grinder and a cutoff wheel like I am, make sure that you have everything held and supported extremely well, and make sure that you do know where your sparks are going and things like that. Once they're cut, you can get everything positioned up and ready to machine. Again, I'm not going to be able to TIG weld this for this video. Maybe in the future we'll come back to this if we end up designing the entire manifold and welding everything together. But the process is relatively simple. If you are a TIG welder, then you should already be familiar with welding stainless, and if you need to do things like purge the inside or preheat or anything like that. All right, so now that this is all said and done, with the exception of welding, obviously, so what are some things that I've learned along the way and would potentially do different or change based on the outcome? So I would say that during the design of the flange, the space for each of the bends is perfect. So if everything gets cut perfectly, then everything fits nicely. However, we know that in reality, things are going to be difficult to cut. You're going to have to do some back and forth. So my suggestion would be to leave a small gap or an offset for the area where each of these pipes needs to fit. So that will simplify things when you're trying to get the cuts done. It'll give you a little bit of flexibility, but just keeping in mind that the ID of, in this case, the mandrel bend will not fit perfectly to the CNC part. So that's one thing that I would potentially do different, and maybe even raise the lip up higher than 1 millimeter, just so that it has a better seating area to make it easier to hold together when you're trying to weld it. The other thing I would say is Get the best possible tool to cut these. So I used to have a sort of one of these horizontal, vertical, cheap bandsaws where you could flip it up in an upright position and mount a table, and they're pretty much junk. The blades are too thin, they twist and they tweak, and you can't really get a good cut out of them. I found that mine bound up all the time when I was trying to cut thinner stuff. So I opted to use an angle grinder with a cutoff wheel specifically for stainless. That works okay. It's just hard to hold and it's messy. So I ended up putting these on a 2x6, clamping them down, and then cutting them that way. It was a little bit easier to control where the sparks were going. Obviously, whatever tool you have at your disposal is the one you're going to use. You can do it with an angle grinder, and you can do it with a cutoff wheel. You could probably do it with a reciprocating saw, but it would be best if you had a decent vertical bandsaw or some other tool that would just do a bit better job with cutting. So that would make your life a little bit easier. I just don't have direct access to that stuff right now, so that makes it a bit more tricky. And I know most of the people at home will probably be in the same boat where you end up having to use things like an angle grinder and a cutoff wheel, which are not ideal, but can get the job done. So all that stuff aside, I think that everything went together pretty well. All said and done, like I mentioned, the mandrel bends were about $8.50 a piece. So we're looking at about $40 for the 4 pipes, and then $90 or about $100 shipped for the CNC flange. Anything else that I would change would likely just come down to the direction that the bends are going. If I wanted to use straight sections instead of the bends, that might have made things a little bit easier, because you can buy one straight section of pipe and then cut it with a template however you want. The template worked out pretty well, the 3D printed template. I think that I probably would have used layout die or maybe a Sharpie instead of the marker that I used, just simply because it just didn't adhere to the stainless very well. But other than that, I think the 3D printed template was a perfect solution for this. So all said and done, I hope to weld this together in the future. I still have some more planning to do on the rest of the manifold that I want to build. So I'm not quite to that point yet where I'm going to go weld this together just to have it welded together. And hopefully I will be able to build the rest of the manifold, and then we can come back to this at some point. But if you have any questions on this, please let me know. As always, thanks for watching, and we'll see you in the next one.